Hello, everyone. I'm Will Alexander, and thanks for having interest in my first ever con talk here at CarolinaCon. I'm currently a red team engineer at Palo Alto Networks. I've got some defensive experience with some SOC work, incident response, and threat hunting. I moved over to the red side because I really enjoy abusing technology. So for the last few years, I've been advancing my tradecraft to become a better operator. My wife and I are expecting our first child in September, and I'm elated to start that chapter of my life. And finally, feel free to reach out to me on Twitter or Discord. During this presentation, I'd like to cover the ins and outs of CI/CD and discuss some notable real-world supply chain attacks to set the tone. Then I'd like to discuss some techniques my team and I use to abuse CI/CD in a red team engagement, which enabled us to moonwalk through my organization's cloud environment. Finally, I'll close out the talk with some DevOps and security considerations being implemented at Palo Alto Networks and general supply chain mitigations. CI/CD is a DevOps methodology used to frequently deliver apps to customers by automating stages of the software development lifecycle. Continuous integration is the process that occurs after a developer checks code into a repository like GitLab or Bitbucket. After making changes, the code is merged into the master branch, which kicks off a build process. The build process creates the needed artifacts, and the code is run and tested with feedback automatically provided to the developer so they can know if their changes broke anything. This process is repeated continuously as all developers work on code for the project. The build and test process is typically executed on a CI/CD runner. In GitLab, the runner is flexible and open source and is written in Go. It can be deployed to bare metal, virtual machines, Docker containers, or Kubernetes, depending on the needs of the developers. The runners are typically ephemeral and short-lived devices that spin up and down only when a build process is executed. I'll talk more about these runners soon. Continuous delivery is the process of packaging the created software artifacts from the CI process and preparing them to be delivered to environments like QA, UAT, or production. And lastly, CD could also refer to continuous deployment, where the process of deploying to the aforementioned environments requires no human intervention. For the remainder of this talk, my focus will be on continuous integration and continuous delivery. Summed up, the entire CI/CD workflow is meant to automate and speed up DevOps while making developers aware of bugs earlier. So there's tons of CI/CD platforms and tool sets, free and paid services in both open source and closed source. And CI/CD is said to have all of these benefits like faster developer iterations and efficiency, higher release quality, and more consistent build processes. Some of these products even claim to lower the risk of security incident by misconfiguration. Well, that sounds like a challenge to me. Well, it sounds like less of a challenge as soon as you introduce a weak link, the human. The threat landscape becomes wide once developers begin introducing unvetted third-party code dependencies or public container images, or even just using extensions for various IDEs. Developers may even be hard-coding keys, credentials, and secrets within projects that could lead to attackers being handed the keys to the kingdom. This doesn't even touch on standard security misconfigurations like overly permissive accounts or faulty firewall rule sets that could play a role in limiting a CI/CD compromise. The SolarWinds breach affected so many organizations because the actors were able to modify code for software updates within the CI/CD pipeline. The Orion source code was modified to include a backdoor, the CI/CD build process was executed, and the software was distributed to clients. Hundreds of malicious NPM packages are being discovered in the wild. The user agent parser JavaScript library was recently compromised with 3 malicious versions, and at the time, This library had roughly 7 million weekly downloads. Attackers operated in the Puriform network for months, preparing their malicious version of CCleaner. It was hosted on the official website and distributed to millions of users over the course of about a month and a half before the company was made aware and removed the malicious version. My team set out to determine the breadth of compromise starting from 3 assumed breach scenarios: a single CI/CD pipeline compromise, a developer installing a malicious VS Code extension, and a multi-pipeline compromise. In the first attack scenario, we worked to simulate a scenario wherein developers are including unvetted third-party dependencies within their CI/CD build process. We backdoored a simple Debian package and worked with the developer to modify his code so that the build process would download and install the malicious package from an arbitrary site. We rolled out our attacking infrastructure, which included a payload server and command and control infrastructure in our own Google Cloud environment external to Palo Alto networks. The developer kicked off the GitLab CI pipeline and the build process began. A GitLab runner was spun up, it installed our malicious package, and C2 was established. Because of the short lifespan of these runners, we opted to background our malicious process in order to keep the runner up. It should be noted that developers may notice hung CI/CD jobs, as this process typically takes less than 5 minutes. The runner was deployed in Kubernetes, so when we landed a shell, we were in a pod. Going into this engagement, we researched methods of pod escapes and privilege escalation in preparation. Turns out we were overprepared. CI/CD variables are a type of environment variables that are meant to help developers. These variables can be used to control the behavior of jobs and pipelines, store values for reuse, and avoid hard coding values in code. To an attacker, the runner environment variables provide a wealth of information. There's a number of predefined variables that include important details about the runner and GitLab resources. One specific variable that we found valuable was the CI job token, which can be used as a form of single-factor authentication to query the GitLab server API endpoints. Any requests made using this job token run with the permissions of the pipeline owner, which is the developer in most cases. This token is not local to the project being worked in. Whatever the developer has access to, the token can be used to access it. It's important to note that this token is only valid as long as the job is running. But since we hung the pipeline, we had some additional time to use it. And so we set out to determine what the developer had access to. The GitLab API documentation became handy very quick. We began by listing out which repositories the developer had access to, then used Git to clone each of them to the runner, then moved them locally. Just as a proof of concept, we automated this process with a tool we dubbed Git Labrador Retriever. We successfully exfiltrated more than 400 projects in minutes. Compressed down, it was just over 4.5 gigs. The developer must have been very busy to work in 400 projects at the same time. Or this is just a typical case of an overly permissive developer account. Funny enough, we crashed our C2 server on the first exfil attempt because the data was too large. From there, we opted to use Updog as our exfil server. We began perusing through the source code offline to further our attack. And it wasn't long before we found hard-coded credentials for an Active Directory service account without multi-factor authentication in place. We used this account to access the internal Jira server and scrape thousands of tickets from our foothold on the runner. After that, we authenticated to GCP and AWS, where we had read and write permissions to numerous projects. At this point, we were happy with our level of access, so we moved on to phase 2 of the operation. In this scenario, we modified a legitimate VS Code plugin to include another binary that would establish C2 when the plugin is installed. During our research, we found that it was trivial to craft an identical looking extension. The screenshot on the left is the legitimate extension, while the screenshot on the right is the malicious one. And as a bonus, VS Code extensions are a great form of persistence, since each time VS Code is started, it kicks off our payload. We worked with a different developer to install this plugin, so there wasn't a ton of overlap with the first attack scenario. Once the foothold was established, and after some initial reconnaissance, we discovered the developer was using the GitLab workflow VS Code extension. With this plugin, devs can browse repositories, create merge requests, and manage CI/CD pipelines all from VS Code. But to do any of this, the plugin requires a GitLab personal access token, which is stored in a database file on disk. On macOS, the VS Code database file is stored in the application support code user global storage directory. We yoinked the database file and used SQLite to carve out the token. We then used the personal access token to query GitLab for group and project variables that the developer could access. Group and project variables are custom variables that get passed to runners during the CI build process. As expected, we found numerous credentials, secrets, and tokens for a number of other CI/CD applications, including an Artifactory service account. At this point, we had rights to upload packages to the internal Artifactory that could be used for further compromise. We also had permissions to modify existing dependencies for further pipeline abuse. Stepping away from Artifactory, we returned our focus to the GitLab personal access token. Again, armed with the API documentation, we were able to commit changes to an existing repository and execute the CI/CD pipeline, which landed us another foothold on a GitLab runner. Rinse repeat the first attack scenario. Back on the developer's host, we began exfiltrating GCP credential database files, some of which belonged to CI/CD service accounts. Using the gcloud command line utility, we authenticated with the stolen tokens and found we could access numerous GCP projects, storage buckets, and Kubernetes clusters. Google has this great feature called metadata managed SSH, which creates a public key and attempts to add it to any compute instance you try to connect to. So with the right permissions, we began spreading into numerous VMs that are not internet accessible by using the gcloud compute SSH functionality. We didn't really execute groundbreaking techniques for GCP post-exploitation, but we did lean heavily on a blog post from GitLab's Red Team, which is a great resource for privilege escalation and lateral movement. Our typical process was to authenticate with a set of credentials, list accessible projects, then enumerate and document accessible services and service accounts, enumerate the permissions of other service accounts, SSH to compute instances, seal more tokens, and repeat the process. By the time we exhausted all of the service accounts that we could authenticate with, we had access to hundreds of GCP projects. At this point, we wanted to use our beachheads within GCP to proxy traffic internally. We crafted a custom Docker image, which used Stunnel to mask SSH traffic as TLS in order to evade firewall detections. This container was deployed to a few VM instances and was used as an ephemeral space to run scripts and interact with internal web interfaces. Eventually, we found a free IPA LDAP server deployed in GCP that allowed us to dump a couple thousand Active Directory usernames and groups. We also used this LDAP server to further validate credentials found during past exfiltration. Before calling an end to this attack scenario, we returned to the C2 from the developer's machine to try to steal his Okta session token. We restarted his Google Chrome session in debugging mode and queried the debugging port. We were able to obtain the Okta token, which was then replayed using Burp Suite, which bypassed MFA and dropped us to the developer's application dashboard. For the final attack scenario, we worked with a developer to modify a CI template so that it would include a custom Linux binary that we wrote. CI templates allow developers to incorporate their favorite programming language or framework into pipelines. Instead of building pipelines from scratch, these templates simplify the process by having parameters built in. The template was used as a way to simulate multiple developers using a single compromise dependency. When the pipeline started, our binary was downloaded and executed. Because of our previous attack scenarios, we knew the runner environment variables were a trove of loot. Our payload simply exfiltrated environment variables to an external web server via HTTPS, and before long, we were sitting on hundreds of keys, API tokens, and Active Directory service account credentials. Without much effort, we gained control of more than 4,000 projects within GCP, which likely would have turned into a full organization compromise given the time for reconnaissance and lateral movement. Instead, we turned our attention to other credentials, one of which was an old GitLab bot account with single-factor authentication. We logged in and we found the bot was a GitLab admin. Although being an admin, the bot didn't have a ton of access to do non-destructive activity. There were no permissions to view or modify repositories, so we used the API to determine the user with the most privileges. The API has an admin-only impersonation function that essentially crafts a personal access token of other users without alerting said user. So that's what we did, and that's how we owned the entire GitLab instance. Although this was likely the largest attack, it was relatively uninvolved. Hopefully, these attack scenarios have emphasized some possible outcomes of supply chain compromises. But these breaches don't stem from a single failure in defenses. There are a number of mitigating factors that we as a red team believe could have prevented the wide-scale compromises. Here are some of the recommendations we made after concluding the engagement. Generally speaking, the top of the list is more upstream and would have disrupted operations, while the bottom is more low fidelity, but still could slow attackers down. In most cases, GitLab runners should not be making outbound connections, especially to health and finance domains that attackers commonly use to avoid SSL stripping. Secrets should not be stored in environment variables. GitLab supports HashiCorp Vault as an external secrets engine. These secret managers should be secured and regularly audited. Don't allow developers to have access to hundreds of repositories simultaneously. Prevent developers from including arbitrary third-party dependencies that have not gone through a code review process. Instead, force devs to use a central artifact repository like Artifactory. Watch for one or a few accounts cloning down numerous projects at once. Monitor highly permissive accounts like GitLab admins conducting impersonation. And there are a few others like checking for Okta replays, keeping an eye on weird cloud SSH events, and regular artifact scanning. But these recommendations may only work in a bubble. Different organizations obviously have different requirements and use cases. The CI/CD pipeline was conceptualized with a developer-first mindset. Speed and convenience are the primary goals. Therefore, it's important for developers and security practitioners to evaluate the threats associated with DevOps. This engagement was my first foray into CI/CD and cloud red teaming, and I really enjoyed it. So I plan to continue research into CI/CD abuse. Earlier this year, the NCC group published a blog with 10 CI/CD attack scenarios. Some of what we executed is covered in their post, and my team is planning to conduct another engagement related to the remaining relevant topics. Hopefully this talk sparked enough interest to have more folks in the industry review their own CI/CD environment. And lastly, I'd love to chat about your experiences with CI/CD. If you've conducted an engagement, went through a security review process, or just want to discuss more about my presentation, feel free to reach out. And I just wanted to give a few quick shout outs. Thanks again to CarolinaCon for hosting and accepting my first ever con talk. Shout out to the 49th Security Division at UNC Charlotte. They're a great cybersecurity club that I was a part of while I was still in school. Definitely want to show them some love. Shout out to Josiah Petekiel, who was our red team intern during this engagement. He's a genius, and we refer to him as Big Brain. And finally, shout out to Richard Penshorn, who joined us for 2 weeks during the engagement and taught us a lot about cloud lateral movement. Thanks.